Okay, we start a new chapter here. You should have some paper out to write some notes. You should start getting used to having a periodic table available to you, right? Pulling it up on a separate tab, or if you want to print out a copy to have sitting in front of you while you go through things. We're going to start referring to that more and more and more. So you should be getting used to having that in front of you and looking at it, okay? So we're doing chapters 4 and 25 together. And that means that when we finally get to the test on this, the test will be over both chapters. And I realize that chapter 4 and 25 seem like they shouldn't go together, but it turns out they go very well together. Once again, if I were writing the book myself, I would have put these two chapters right next to each other. But as it turns out, they're not. But that's all right. So when we start off notes, remember, I always give you a list of the objectives for the chapter. These objectives for the chapter are a good checklist of things that you should be able to do before we get to the test. These are also listed on our daily agendas, so you can always see what these objectives are supposed to be without having to go back to this video every time. All right, our job here today is to start talking about the basis of all matter. Since we're studying matter, and we just spent chapter 2 talking about the different types of matter and how we classify matter, we need to break matter down into the simplest part, right? And we know the smallest, simplest part of all matter is called the atom. Now, how do we know that, and where did that come from? This idea of the atom goes way, way back. Okay, it goes way back, thousands of years ago. There was an ancient Greek philosopher by the name of Democritus. Democritus, being a philosopher, was a guy that was sort of like a teacher, right? Except that he didn't have any formal school that he taught at. Most of the time, philosophers were people that just spent time within the community talking with other people. And they would talk about just ideas and concepts and things that would pop into their head and then talk about them with other people. Right? And people thought of that as a teacher because they seemed to be pretty smart because they kept coming up with all these curious ideas. Now, none of it was based on science because they weren't doing any experiments to prove that they were right. They were just simply giving ideas, all right? So Democritus was, let's say, one day having a conversation with a group of people. And he comes up with this thought, this question. And he says, I want you to imagine that you have a piece of pottery, right? It's kind of a vase. And you were to take that vase and you were to hit it with a hammer. What would happen to it? Right? And of course, everybody would be like, well, of course, it would break into pieces. Yes, right. We all agree that would break into pieces. Okay, now I want you to take one of those pieces. This is all happening in your head. We're not really doing this. I want you to take one of those pieces, imaginary pieces, and I want you to hit it with another hammer. What would happen to that piece? Well, it would break into smaller pieces, right? All right, now, let's keep going with this situation. I want you to keep taking the smaller pieces now, and I want to keep hitting them with a hammer and breaking them into smaller pieces, and then hitting them with a hammer and breaking into smaller pieces. Now, how long could you keep that up? That's what he would say, right? How long could you keep that up? And some people might say, well, eventually the pieces are going to get so small that you can't really see them anymore, right? Because it'd be like little pieces of dust. That's really small. It's really hard to see those. And your hammer would be so big it wouldn't be able to do anything to the dust. So Democritus says, okay, I want you to then imagine that you have a couple of superpowers. Let's imagine that you can see even the smallest things with no problem. You don't need a microscope or anything. You can see anything, even at the really small level. And let's imagine that you can make your hammer as small as you need it. So imagine that you can keep seeing these smaller and smaller pieces, and you can keep hitting them with a smaller and smaller hammer. How long do you think you could keep this up with your new superpowers? And there would be usually two answers to this. There'd be some people that say, well, you should be able to just keep going forever then. If I have the power of seeing smaller and smaller and smaller, no matter how small it gets, and I keep having this power of making a smaller and smaller hammer, no matter how small it gets, I should be able to keep going forever. And other people would say, you know what? No, I think eventually, even with those superpowers, you would eventually get to something that's so small you couldn't break it any further. It would just be the smallest thing ever. And Democritus was on that side of it. Democritus thought, yeah, I kind of agree with those people that say, I think we would eventually get to some smallest thing ever. No matter what it was, whether it was a vase or anything, no matter what you break, you would eventually break it down into something that would be the smallest part. And in ancient Greek, he called it the atomos, right? Those are the atomos, the very smallest particles of all things. Now, he only had an idea. He had no way to show that there was any evidence that he was correct. And several years later, there was a much more famous ancient Greek philosopher by the name of Aristotle. Hopefully you've heard of him at some point. He was very famous. Everybody in Greece knew of him, and he had a lot of respect. A lot of people thought he was a very, very highly intelligent person. And what he would say usually influenced a lot of people. And he was on the other side of this argument. He believed that no, if you really had these superpowers and you could see really small and you had these really small hammers, that you should be able to go forever. What should stop you? Why should you believe that there's some stopping point to this? And so he believed that there was no such thing as an atomos. And since he was really influential and people really respected him, most people said, yeah, you know what? That Aristotle guy is pretty smart. I'm going to go with him. In fact, he was so influential, it was 2,000 years before somebody finally challenged that idea, right? Can you imagine that if you said something to somebody and they went ahead and said, you know what? That's the way it is. And people for generations to come, for thousands of years to come, believed what you said? That would be incredible. That's how influential Aristotle was. But sometime in the late 1700s, early 1800s, John Dalton, very famous chemist, John Dalton went back through some of the books and whatnot that he was reading, and he read about this guy named Democritus, and he had this theory of these atomos, which he kind of translated in English to just atoms. And he thought, you know what? That would actually make a lot of sense. That would explain a lot in chemistry if we did have these things called atoms. And so he came up with what we would call today the modern atomic theory. And it is the basis of everything in chemistry. So it's really important that we talk about what this atomic theory says. The first part of it is exactly what Democritus said all those years ago. All matter is composed of extremely small particles called atoms. Again, he doesn't have any direct evidence of this. Nobody has a microscope in the 17 or 1800s that can see individual atoms. But let's go through this, and you'll kind of see how he pieces this together, and it helps to explain things. He says, all right, so if everything's made up of atoms, and we have elements out there, then why are the elements different from each other? It's because they're made up of different atoms, right? Why is gold different than silver? Because gold is made up of gold atoms, and silver is made up of silver atoms. That would certainly help it. If everything could be forever broken down, then what would ever be the difference between gold and silver if they're made up of the same infinitely small particles? Doesn't make any sense, he says. So there must be a smallest part, and these atoms, these smallest parts, must be unique to each element. He also says that if we're going to come up with this concept of an atom, it's got to be the smallest thing. You can't go any further. They cannot be created or destroyed or divided, right? Different atoms could combine to form compounds. So now if you want to try to explain, oh yeah, where does water come from? Water is not an element. Water is actually two elements that have been combined to form a compound. And then finally, and I think this is one of the most important parts, is that chemical reactions are really just atoms rearranging with each other. Now, imagine, before this, nobody understood what a chemical reaction was, and in fact, most people believed that it was more of a magic, right? That there was some kind of unknown force causing things to move and turn into something else. In fact, that's what the alchemists were thinking. They were thinking, oh yeah, there's some kind of magic formula that if I just figure it out, I can turn this rock into gold. And eventually, people like John Dalton said, well, that's ridiculous. Because we're just talking about atoms. Atoms are just simply rearranging and moving around. You can't create them or destroy them or divide them. You just rearrange them. And it takes the magic out of it, and that's a good thing. You don't want to think of everything in life as just magic, because then you don't have any clue how it works. And now he says there's a way we can understand how this works. So these are really important. I want you to understand and know Dalton's atomic theory. Because like I said, this is the basis for everything that we do in this class, in chemistry. The other thing I want you to realize is that atoms are so small. And it's really, really hard for me to explain how small. I'm going to put a video up on Edpuzzle. It's short, it'll be like 10 minutes. But it's going to go through and it's going to give you a size comparison between the biggest things in the universe and the smallest things in the universe. And you get a good sense of how small we're talking when we talk about atoms. And I'm not going to show the video, obviously, right now. You can watch that on your own on Edpuzzle. But I do want you to realize that it has only been in, let's say, the last, 50 years that we have developed the technology to be able to see individual atoms in a microscope. Right? Relatively recent. So these are both pictures of individual atoms. This is an atomic force microscope that you see here. By the way, this here is the tip of a very, very, very tiny little needle that's pointing and moving individual atoms. And it looks like it's huge. Okay? But this would be so small you wouldn't be able to see the tip of it. And these are individual atoms that are being manipulated and moved around. And this picture here, you can see, is a picture where they took the individual atoms and they were able to move them around enough that they actually spelled out SI, which of course you know because you've memorized all those elements that I asked you to memorize. That stands for silicon, right? SI is the abbreviation for silicon. And so these are silicon atoms that they were able to manipulate and move. But you notice, how good are these pictures? How clear are these pictures of atoms? Don't they just look like little fuzzy balls? Right? I mean, it looks like somebody just took a really bad picture of some lights or something like that. Or they took a really bad picture of like some scoops of ice cream. I mean, it doesn't look like much. Why doesn't it look like much? Because even with these really, really high-powered microscopes, these atoms are still so small that it's really hard to get a handle on what we're looking at, okay? And what's even more important is that we've never, ever seen inside an atom. However, we have a pretty good idea what it looks like inside. And we're going to get to that in the next time.